So today I will share our experiences of working to develop this ER theory and also apply this to develop some systems and platforms which can be accessed worldwide for professional services. So our research is mainly two parts. One is the ER theory, and another one is application. So over the last 40 years or so, we have been working from different perspectives on applying the theories from different domains, from decision science, system science, computer science, and also AI to different domains in applications. So today, we really try to explain the origin of why we have been conducting the research. So many years ago, we worked in a kind of industrial systems, in process engineering, systems engineering, and control engineering, try to apply methods and theory in operational research, decision science, system science, and control theory to deal with large-scale optimization and control problems in large-scale industrial systems. At the time of application, we faced some challenge, which is how to handle and model and use both qualitative and quantitative information to support modeling, optimization, decision-making, and control. So this was the challenge. So we developed some models we call hierarchical analysis model to try to support this analysis. Then we also developed algorithm to support the analysis and also apply this to different areas, different domains by using rule-based AI technique and also utility theory in decision science to support assessment and also decision-making of different things like product design, like production management, and also risk analysis. So this is a lot of applications. So today I only show you one tools we developed, which we call intelligent decision systems, which can be downloaded from my personal website. It's mainly for supporting multi-criteria assessment and multi-criteria decision-making for very different domains. This is for company supplier assessment and selection for Siemens procurement. And you can see it's an old Windows system and developed on Visual C++. In this application, we used a lot of criteria, both qualitative, like financial soundness, ethical, and other kind of criteria, and also quantitative criteria like cost and others to support supplier assessment. So this was also applied to other areas. This is the first element of our ER theory, ER approach for supporting multi-criteria assessment. The second one we call belief rule-based methodology for supporting system modeling, optimization, learning, and also prediction. So this work was started when we tried to apply the traditional AI techniques like rule-based system for supporting the analysis of risk and also safety in large mixed-order engineering product like oil platform or large ships like warship. So how to use multiple attributes to support the safety assessment of large systems. For this example, if multiple attributes can take some different values, the assessment can be uncertain. So it may not just be average, fair, or good. Some opinion says it's fair to a large degree, 40%. Some says poor, 20 degree, and the other would be 10%. But the consensus is not good anyway. But this assessment is not complete either, because some people may say this is just below average, safety is below average. Some may say it's just not good. So as you can see, for this kind of uncertain assessment with probability assigned to individual outcomes or consequences, and also to subset of outcomes, we call this ambiguity. But how to handle this? This we call belief rule or basic probability distributions to model the uncertain assessment of safety. So this idea was generalized later on to try to model a kind of systems when we have nonlinearity, uncertainty and ambiguity. So this maybe we have multiple variables or inputs, or we call attributes. Each can take different referential values. Then the consequence can be multiplied well from D1 to Dn, but the assignment to consequence can be also to subset of a consequence. So this kind of consequence we call B kind of distribution or basic probability distribution. And also for each rule, we could also have reliability or weight. And for each variable or attribute, we can also have weight. For this kind of system, those kind of parameters can be learned using data or can be assigned by using people or experts' judgments. And then we develop a system as well to support its application to different domains in engineering and also in finance. So I will show a few examples later on. So this is one very simple example. We have also developed some platforms, which is open source platform. For this one is developed by a group in University of Jyväskylä in Finland, which is open source. You can apply this. This is one example. For example, the blue one is a real non-linear function, and the red one, for this case, is just assigned by using a BIB system, and the parameter was assigned by a researcher rather than trained at all. And you can see the fit is not very good. However, if we train those parameters alone, we can really improve the performance of the system. And if we allow both the parameter and also the structure of the model is trained, and you can see we call this referential values to be trained as well, then they converge to a kind of a typical points like the optimal and also minimal and also flexible point. Even some redundant kind of referential value can be identified. So that means the system can simulate very non-linear system with very limited or a kind of parameters. This is one thing. Another one can be if the system output is, as you can see, uncertain with intervals and change over time. This can only also be modeled by using a very simple BIB system, because each rule in the system can model ambiguity, which can model the interval or the change of the system. So one BIB system can model very non-linear and uncertain system output. So we have used this technique to apply to many kind of different domains. The third element of the theory we call ER rule is for combining multiple pieces of evidence with both weight and reliability. This origin is based on Bayesian rules, and you can maybe you know already. Bayesian rule is very widely recognized as someone said the idea, someone said it's very desirable inference framework when the data is perfect and the judgment is also available. So the reason is we have probability from the data, we can get it, and the whole process of inference is based on trying to find the joint probability and then find the posterior probability. This we call Bayesian principle. So Bayesian rules has been used for data analysis, for building systems, even like large language model has also used Bayesian theory to generate outcomes. So our work is based on Bayesian theory. However, Bayesian inference has some limitations. This is one example proposed by late Professor Zadeh. He criticized not direct to a Bayesian inference, but to we call evidence theory proposed by Professor Schaefer in. He was working in Princeton University at the time. Then he later worked in other universities like Kansas and also Rutgers University in the USA. And also he used his work based on Dams's work. But as you can see, in this example, we have two experts who provided judgments on kind of disease a patient may have received. So one said, almost certainly it's meningitis, but he didn't really exclude brain tumor, although this is very, very small probability, and he didn't think it's a concussion at all. A second expert provides very conflicting kind of judgments. So he says it's almost certain it's concussion and exclude meningitis, but he's not sure about brain tumor. Although this 0.01 probability is seems plausible, but this can be even smaller, towards 0. But even it's very small, this is towards 1, then the conclusion is it's for certain the posterior probably is 1. This we call a kind of counterintuitive conclusion from this kind of judgment by combining the very highly conflicting information. So this seems irrational, and there's a lot of criticism on how to use Bayesian inference or kind of probabilistic inference to get conclusions. But is this a kind of criticism fair or is well-based? This is our research for many years. So I can just give one simple example to show you how this can be resolved and why it can be resolved. We also have a platform developed by a research group in Beijing University to how to apply the ER rule. And also the paper was published about 12 years ago on this subject. So the main kind of thinking is no expert would be 100% reliable. No data would be 100% accurate. This is the starting point. So that means when we assume it's 100% reliable, it's not really a realistic assumption at all. So here, for example, we assume each expert is only 95% expert kind of reliable rather than 100%. Then we can discount the judgments given by each expert. For example, the first one, we can discount these judgments. And what's remaining is, as you can see, once we multiply the reliability or weight of the first expert, then this kind of judgments over the 3 diseases, their probabilities are not added to 1 anymore. There's remaining probability which we call unreliability or untrustworthiness, which is now in this case 0.05. Here is assigned to a new dimension, which is a power set of those disease. It can be any of this disease or any subset of the disease. So we call this a power set. This is a new kind of space we call evidential reasoning probability space or ERPS. The first one we call this system input probability space or SIGs. So in ERPS, we also can model other expert judgments using, we call this generalized or augmented probability distribution with a power set is an added or extra dimension of the original probability space. And then we can find this joint probability, and you can see, although the second expert, so this should be M2, the second expert doesn't support meningitis, but his assessment, his judgment is not fully reliable. So this 5%, which is he given to the first expert to decide. So if you multiply the first expert's judgment, 0.9405 by 0.05, then you can have this joint one. Similarly, you can find the other joint ones. So this is joint probability in the ER probability space. Then you can find the posterior probabilities in the same space. And then finally, we can project the assessment in the ER space back to the original, we call this systems output probability space or source. And you can see now the conclusion is the judgment is both meningitis and concussion would be equally likely to happen because both experts support them. But the middle one, the brain tumor, is also very remotely likely, but the likelihood is very small as well. So this seems rational, should be rational, these judgments. So this is our third element in ER theory. The most recent one we call maximum likelihood evidential reasoning, which is really for generic probabilistic inference with imperfect data. So in this case, we tried to model not only randomness as a Bayesian inference is modeled, but also ambiguity, and we just assumed. And also, if information is not fully reliable, then we can also model this as unreliability or trustworthiness. That means those three types of uncertainties can now be modeled in the same framework, which we call make framework. We use the three different probability spaces to make sure the whole process follows the robust scientific principles, and the whole process they generate probabilities as well. And also the variables like the weight of any data source, and also reliability of any evidence generated from the data source can also be learned from either from data or from judgments. So this framework we call Maker framework can be used as a kind of generic framework for supporting probabilistic inference with imperfect data. So this we showed how the data can be generated as evidence. And also how we can justify the whole process by following the well-recognized scientific principles. And also we compared our new findings with what has been researched over many years with traditional theory. And we have also submitted our most recent research on how to support disjunctive reasoning when any condition is met, what would be the conclusions. So this is our theoretical research. If I use one diagram to summarize what we have been doing on our theoretical research, its origin or its basis is Bayesian rules. And I just say Bayesian rules is principled rules. It's widely used. However, it has limitations. For example, it only, as I said, only allow the probability to be assigned to single hypothesis, and also both data source and any evidence generated from the data source are assumed to be fully reliable. So this was not really the case in real or practical applications. The Dempster in Harvard, he kind of generalized Bayesian rules to some degree. He allows the probability to be assigned to subset of the hypothesis. So that means ambiguity of judgment or imperfect data can now be precisely or accurately modeled in a probability domain. And we use Dempster's idea to develop our evidential reasoning approach for supporting multiple criteria decision-making. That was from another dimension. Then in the last 15 years or so, we have extended this research on ER approach to ER rules for generic probabilistic inference with a kind of information. Now, both the data source may not be reliable, and the evidence from data source is not reliable. Their reliability may not be equally the same. They can be different. And most recently, we have generalized this idea to support generic probabilistic inference with both dependent evidence and also by optimally training the parameters for supporting both conjunctive reasoning and also disjunctive reasoning. So in real systems, this may be the case. This is a summary of the foundation of the series. And the main findings may be summarized by two main theorems. This one seems complicated, but actually it's very simple. That means we try to find the posterior probability, and by finding the joint probabilities in the ER space, then all the findings, all the probability generated, we have a kind of trustworthiness. So this is described in our recent papers. And another one is we support disjunctive analysis. This is another foundational theorem. The only difference now here is we generate the joint probability for disjunctive reasoning, which of course is based on this conjunctive reasoning. Sounds a little bit complicated, but once we can calculate the joint probability, then we can also calculate the disjunctive joint probability. Anyway, I don't want to say too much about the theory, so now I only use the same example, generalize a little bit, to explain how and why it works. So the same example, two experts assess the patient, whether the patient has meningitis, a brain tumor or concussion. Here, as you can see, we assume this expert one is almost certain it's meningitis, but he has excluded concussion. So any direct assignment to concussion is 0. any indirect or possibility to a concussion is also zero. So concussion is excluded by the first experts. Although the first expert doesn't really assign any probability to brain tumor, he doesn't exclude it either. So this point one we call probability for ambiguity is a kind of a probability which cannot be reassigned to either meningitis or to brain tumor at all. This is we call Damsel principle, because this point 1, is a measure of ambiguity or unknown by the first experts. Similarly, the second expert assessment can also be to a kind of ambiguity between brain tumor and concussion, but the second experts exclude meningitis. So as you can see, the two experts are still in conflict with different kind of interpretation. Another one is each expert assessment are not reliable. This WI means the ability of expert one, historically his assessment of the disease can be trusted to about 72%. But in this case, and he is very careful to allocate those probabilities, then the reliability of this assessment is represented by this distribution, probability distribution, is more reliable than his own abilities. Then this can be turned into to what degree this assessment can be trusted. Similarly, the second expert can also be modeled by his reliability of ability in assessment of those disease, and also by his reliability of providing this conclusion of diagnosis of the patient. And then we can now use the original information with, as you can see, the basic probability distribution to model both randomness and also ambiguity, and also with reliability in the new space, ER space. Then new dimension, so as you can see, we now use the trustworthiness to multiply the original assessment to get new probability to measure to what degree the first experts support meningitis assessment, which is trusted anyway. Then what's left is, and you can see those together is 0.8. So what's left is 20% is given to the power set. So this is measured in the power set. It will not be allocated by this first expert at all. It's left there for combination with the second experts. So the second expert left 40% to be unsigned. So this 40% or 0.4 probability is the kind of right of the second expert given to the first one to decide. Then we can use the same idea to find the joint probability. For example, for meningitis, although the second expert given 0 probability, however, he's uncertain about this. So 40% is his residual right, or is right left for the first experts. So power set intersect with meningitis is still meningitis. So that means the probability of the first experts multiplied by what's left from the second experts, we get the joint probability for meningitis. For brain tumor, both experts don't support it at all, but indirectly, and you can see the first one doesn't really exclude it, and the second one doesn't include either. So MB intersect. BC is actually B, it's a brain tumor. So this is how we get the joint probability for brain tumor. So we can explain the same probability for all others. Then we can also find the posterior probability in the ER space to identify the probability distribution in this ER space. And you can see, just divide the joint probability by the sum of all joint probabilities to get the posterior in ER space. Then to communicate and explain the result, we project the result from ER space to the system output probability space source. And you can see now we got a conclusion. So to a large degree, both experts support the meningitis kind of diagnosis, because the first expert is more reliable, and his almost certainly it's meningitis. The second one, although he doesn't really support it at all, but his reliability is much lower. So this is how this probability is assigned to a large degree. But the second expert opinion is still recorded. So 27% is still given to a concussion. It's possible. So for this kind of conclusion with probability assigned to individual disease with some ambiguity to either meningitis or brain tumor or even to brain tumor to concussion can be used for follow-up decision making. So this will be useful for supporting decision making and uncertainty with different kind of course, origin of information. Anyway, this is our introduction about our theoretical research. So how to apply this theory to real applications is our concern. So in real application, especially in finance, in insurance, and also in healthcare, this is our focus in the last 10 years of our application. We identified there's some needs for trusted AI applications. First, we developed some explainable decision systems for healthcare and also for finance. More recently, in the last number of years, once Jian-AI is now really dominating, we also consider how to turn this XAI-DSSs into ER agent to make sure that means any conclusion generated from our system should be, first of all, justifiable. It can follow the scientific principles. Any regulations in the UK and also EU, for example, GDPR, and also any ethical frameworks applied by national or international bodies. And also any conclusion must be traceable from the original data to the final conclusion, step by step, must be traceable. And each step, any sub-conclusions must be verifiable, must be accurate, it's valid, and also genuine. Finally, it must be, of course, inspectable and also defendable or auditable. Otherwise, we can't use it in our high-stake area like healthcare, finance, and insurance. So I only want to, maybe time is not flying, I only really show two examples. One is very simply is for low underwriting. So low underwriting is for one company in Greater Manchester, Together Financial Services. They had a lot of kind of requirements from national regulations to follow the regulations. So a lot of variables to follow, but internally they have internal policies to follow. So they choose multiple attributes to support the loan underwriting. So the underwriting, the key idea is try to use a belief rule-based system, initially by the experts, then trained by the data. This is one simple example with just 3 different attributes. And for this very simple systems, we could use maximum 24 rules to model the expert judgment. For example, if those 3 attributes meet certain conditions, the conclusion may be to a large degree should be founded, but it can also be rejected, and also more information would be needed. For this kind of conclusions, then the underwriters can take further actions. This we call uncertain or heuristic rule. Most rules are like this, but some rule would be more certain, or we call this factual rules or packed rules, because as long as one attribute meets some conditions, for example, affordability is not really likely, then the conclusion is very certain or very direct. It's just reject. So this is we call factual rule or certain rule. And also this kind of rule can reduce the rule base dramatically. For example, this rule can be half this rule base. And also this other attributes can also take into account to minimize or reduce the number of kind of rules. So as you can see, the real system has many more attributes, so it's more complicated, but all rules are traceable and can be identified. So this system is described in the paper because the company allows us to publish the details, so this is available. The second one is the most recent one, is ongoing. We use ER agent to do it because it's more actually meet what we say about agent. Because professional judgment in insurance is a kind of decision-making process by using evidence which can be in conflict, which can be incomplete or ambiguous. So the conclusion could be inconsistent for inconsistent kind of conclusions, we may see a lot of problems because we can see there's low confidence causing delays of decision making or very risk-averse decision making. And also, inconsistency can cause other problems like friction among colleagues or unfair treatment to the clients. So the long-term issue is if we have inconsistent kind of decision making, then the credibility of the organization would be put in doubt. This is not really what we want. So the main goal for developing the kind of system, or we call now agent, is to not only to automate the judgment or decision making, but more to provide a reliable and inspectable or auditable, defendable professional judgment and decision making. So the theory we just discussed, like ER theory or BRB methodology, really are well matched to the requirement of professional judgments and uncertainty, because the belief degrees, as we said, or probabilities can allow incomplete, conflicting, qualitative kind of information to be modeled, expressed without any forced kind of precision or without unnecessary assumptions at all. And also the rule base can be used to encode the expert logic, can be understood by experts like traditional AI systems. And now, of course, it's more flexible because we can allow them to interpret or set the threshold exceptions, and then multiple rules can now be combined by evidential reasoning so that the output is still probability, is easy or straightforward to understand, and can be justifiable. And also we can support the non-linear process and the uncertainty. So the whole process, as we can see, is explainable. All the rules, weight, and evidence can now be explained as a decision trace to experts or any stakeholders. So the system is something like this. We use a large language model to extract either attributes in the model building stage, and also data when we try to apply this to assess individual system or a kind of objects. Then we can use decision science, or now we call this ERBRB decision science layer, to make sure the judgment, the reasoning process is robust, is scientific, and also is defendable and traceable. So the whole system is designed for regulated decision making, so it can meet the regulators' requirements for the kind of decision making in the regulated market. So I just want to show the system. It's developed by a company which is Agentive X. Let's just show this one. Okay, it should be here. Okay, it comes. So 2 2 0 0 1. So this system has been developed by Agentive X in last maybe several months. This is for the data is okay. We can show this, not confidential. I just show you one example, two examples. The first one, and you can see this is a kind of broker's example. The client is a company who is applying for insurance from different insurer. Those are two insurers, and you can see the assessment of risk and also premium are different for the two insurers. So the system support maybe one of those insurer could be the choice by the company. The first is maybe low risk but a very high premium. The second, slightly higher risk but a very lower, much lower premium. So if you look at the assessment of the risk for the second say insurer, and you can see here the yellow means it's a medium risk, the green means low risk, red means high risk. If you look at the high risk, then you can search for the document by using large language model, and you can see the information can be identified very quickly. Should be okay, yeah, very quickly. So this is the reason why the entity scope is high risk. So if you look at other dimension, you can do the same thing. all the reasoning is based on the ER and the BIP engine. So the search is done by the large language model. Okay, thank you.